Okay, we can start.
Okay, welcome everyone to today's One World Property Seminar. Before I introduce the speakers, just a reminder that next week's speakers we have Matthias Eber and Jan Maas. And again, just a second reminder about during the seminar today, if you'd like to ask questions, feel free to type them in the chat, and Alessandra and I will monitor the chat and relay the questions to the speaker if necessary, or also if there are other experts in the audience, please feel free to answer each other's questions as we go along. Okay, so in that case, I'd just like to, I'm very pleased to welcome Fredrik Viklund from KTH to give our first talk, which is on interplay between Dirichlet and Loeffler Energy's cutting and welding operations.
Right, thanks a lot. Thanks for the invitation. It's a real pleasure to be here in this sort of special way. Right, so let's see. So this is the first now of two lectures that report on some joint work between myself and Wang. So Yilin is giving the second talk. However, for actually most, or at least half of this lecture, we'll give some background material and some definitions that we need to somehow discuss the main results and or the main new results. And only in the second part, I will talk about our joint stuff, right? So one, I think, really nice feature with this Loeffler Energy and the story about Weil-Peterson quasi-circles is that actually it fits into several other different stories in very nice ways. So the question is somehow which one to emphasize. And but for this audience, I think also for given our sort of initial motivation for this project, the answer is quite clear. So we somehow, at least for these talks, we are thinking about this as being part of random conformal geometry. So what is that? Well, by this I mean essentially the analysis of various structures, primarily geometric ones, that arise when you look at scaling limits of lattice models in statistical physics, so planar ones mainly. So these are often rough, random geometric objects that we, well, this has been a big theme in probability, of course, over the last 20 or so years, and I'm sure there are many experts in the audience also, but this is somehow how we consider these results part of it mainly. And well, of course, it's a long story, and I'm not going to go into any details here, but just we'll just mention or discuss two of the sort of main players from random conformal geometry that are also important to us. So the first one is the Schramm-Loeffler evolution. So this is a kind of stochastic process that describes scaling limits of interfaces in critical lattice models and certain self-voiding random walks. So for instance, here we see a loop-raised walk, and here is an easing interface. So these, the ones to the left and right, are drawn by Malin Forsström, by the way, simulated by her. And okay, so these SLE curves were discovered by Schramm now a bit more than 20 years ago, so they've been around for some time. And the way they are built or constructed is by feeding the Loeffler equation just a standard Brownian motion. And there is a parameter, this variance of the Brownian motion, kappa. And if we feed this Brownian motion times root kappa into the Loeffler equation, what we get is a curve running in the upper half plane connecting the origin with infinity. Okay, and somehow this curve that comes out of the Loeffler equation, the way it looks depends strongly on this kappa parameter. So, you know, if you increase kappa, you get a rougher curve here. Okay, so these are conformally invariant random fractals, and the idea is that different kappas correspond to different lattice models, and you can prove scaling limit results and so on. So there are this, you know, this is a big, there are many results that I will not discuss. One thing I want to mention though is that a nice feature again with these SLEs is that they are really amenable to computation. So you can use them, you can analyze them, and in this way learn about the lattice models. And so using SLE techniques, many sort of predictions that have been done about lattice models with non-rigorous methods could be interpreted and proved rigorously using SLEs. Okay, and there are links to other descriptions, these sort of more field theoretic stories that physicists like to use. So let me now stop a little bit and sort of discuss this green cloud here that's called the Loebner equation. So what is this? So this is another a device that is rather important in geometric function theory. So it celebrates, I guess, 100 years in 2 years. So the original paper was in 1923. So for the purposes of this talk, we can think about this as follows. So we are given a continuous function. Let's assume it's really smooth for the moment on the real line, and then we feed this or plug this into a differential equation that looks like this. So there's a starting value. So f naught is the identity is equal to z here. We get is a family of conformal maps f sub t such that for each t, f sub t maps the upper half plane onto the upper half plane here minus some, as t increases, some growing compact set. And if this input, this yellow guy, is sufficiently smooth, then this compact set is actually a curve. And right, so that is growing like this. And the growth point is the image under this conformal map f sub t of this lambda of t. Right, and you can also go in the other direction. So starting with a suitable curve, let's say a simple, nice curve in the upper half plane, you can consider this family, these conformal maps from the complements of the curve as you sort of slit the plane more and more according to this curve, and then you look at the pre-image of the tip under this conformal map, and that gives you a continuous function on the real line, and then it's a theorem that this family of conformal maps satisfies the Loebner equation like this. Right? So there is this Loebner equation sets up a correspondence between these real-valued, what we call driving functions, and corresponding curves. All right. And again, these curves that you get from this version of the equation, they grow in the upper half plane and they connect zero with infinity. So we call them chords in this case. Okay, there are also other versions of the Loebner equation. There is a radial version which describes if your driving function is nice, curves growing, let's say in the disk, but the main thing is that it's targeting or growing towards an interior point instead of a boundary point. That's called the radial version. There's also a version that will feature quite a lot in Yilin's talk, that where the input data is not actually a function, but rather a measure. So in this case, one can at least imagine that the corresponding growth happens sort of in many places at the same time. So you can somehow grow everywhere simultaneously. And then you have to put in a measure here and you integrate the equation instead. Okay. So there's quite a lot to say about the Loebner equation. It's an interesting object from the sort of analysis perspective. But the main thing I want to say here is that actually this correspondence between driving function and curve is pretty delicate. And just to give an example, there's actually no known sharp condition on lambda to guarantee that it generates a curve, because it's not always the case that if you plug in a continuous function, you get the curve. Okay. For example, in the case of Brownian motion, there's no, at least to me, known condition that you can check that the Brownian trajectory satisfies almost surely that would guarantee that you get a curve from the Loebner equations. In order to prove that the SLE curve is indeed a curve, you have to somehow work with this family of conformal maps and do estimates on that and so on and so forth. Okay, so that's the Loebner equation. So this sets up a relation, a correspondence between these continuous functions and curves. So the second sort of main player is the Gaussian free field. So this is something that's also very well known to probably most of you, or maybe all even. But anyway, let me say a few words about it. So it's a canonical model of a random surface. And one way to, but it's not really a function. So one way to think about it is that it's a bunch of Gaussian random variables that's indexed by test functions living in some domain D, such as the unit disk, let's say, and these Gaussian random variables have mean 0, and the variance is equal to the Dirichlet energy of this test function. Okay, so it's also possible to think about the GFF as being a random distribution, a random element in a Sobolev space, for instance, with negative index. Okay, and this one way. I mean, for a physicist, you might say that, well, the Dirichlet energy, that's the action corresponding to this field theory, this GFF. For a probabilist, maybe it's more natural to say, well, okay, this Dirichlet energy appears if you try to prove a large deviation result for this Gaussian process. So this large deviation rate function is equal to a constant times the Dirichlet energy. So probably 1/4 times the Dirichlet energy. Okay. So we have a result like this, and this we will return to a little bit later, but it's somehow fine to keep this very loose at the moment. So a big theme in, well, in probability, and in particular in random conformal geometry for the last 10 or so years, has been this emergent picture or idea that actually these SLEs and the GFFs are really closely related. So in some sense, the GFF is the natural habitat of SLE. So this is somehow where they naturally live. And the way to make this precise is through coupling theorems. And well, there are several such results. And well, due to, for instance, Dubedar, Sheffield, Miller, Sheffield, and others. And so let me very quickly and well, informally just try to sketch out how these, there are somehow two main directions where such results go. So there are somehow two main couplings in some sense. So the first, the reverse coupling, so reverse here refers to a version of the Löwner equation, the reverse time Löwner equation, aka the quantum zipper. So here somehow the idea is that you have what is called a quantum surface. That's basically a GFF with maybe some added log singularities that's indexed by or that's living over some domain D, and you have also Liouville quantum gravity measure attached to this domain, and there's a transformation law also when you sort of switch coordinates in such a way that this attached measure somehow transforms nicely. So what Sheffield proved was that, very roughly speaking, if you take such a quantum surface, whatever it is, but you can draw on it an independent SLE curve, and then this SLE curve in some precise way will cut this quantum surface into two independent quantum surfaces, okay, with parameters that can be computed. It's also possible to go in the other direction, so start with two independent quantum surfaces and somehow glue them together or weld them together in order to get a new quantum surface plus an SLE curve in the middle. Okay, and there are these parameters here. There's a gamma and there's a kappa, and they are somehow related here. And the main thing to notice is that as kappa goes to 0, gamma also goes to 0 with this rate. Okay, so the other type of coupling is very different. So this is called often the forward coupling or imaginary geometry framework. So here the SLE is not independent from a field, but rather it's actually a measurable function of the field. So very loosely speaking, heuristically, we can think about the SLE as being a flow line of a vector field that is somehow gotten from the GFF. Of course, this doesn't make literal sense, nor does this here, because the GFF is not a function, it's a distribution, but somehow one can still make sense of this. And this is a really powerful framework. I mean, it allows you both to understand somehow geometric properties of the GFF, and also you can use this to prove things about SLEs and so on. But part of the original motivation for this work with Yilin was to somehow try to better understand these stories from an analytic perspective, using these tools of Löwner energy that I'm coming to in a second. Okay, so let me now switch gears a little bit and go to the more deterministic world and define the Löwner energy. So what is this? So let's we remember the Löwner equation in the chordal version that I described. So we have this correspondence between a curve in the upper half plane that connects 0 to infinity and this continuous function, right? So if we have a chord in the upper half plane, we can do this procedure and somehow recover this driving function. And then by definition, the Löwner energy of this chord is equal to the Dirichlet, the one-dimensional Dirichlet energy of the driving function, just like this. And this was defined by Yilin in her thesis, but was also considered independently and not really systematically in the same way, also by other people. And this is defined in can be defined in any domain by just well, if you have two marked boundary points and a simply connected domain, and you have a chord running between these 2 points, you can just map to the upper half plane with well, one point going to 0, the other point going to infinity, and this mapping is defined up to a final scaling. But maybe this can give us an exercise to check that if you rescale your curve, actually the energy doesn't change. So this is because of this sort of Brownian scaling that is placed nicely with the Loebner equation. That's basically the same reason that SLE curves are scale invariant in distribution. Okay, but this energy does depend on the ambient domain. So it's not, at least not in this setting, it's not sort of an intrinsic quantity for the curve, but it depends on which domain the curve is living in. Okay, so the simplest possible example, I suppose, is if the driving function is for the curve is identically 0 in the upper half plane. So that means we are tracing out the imaginary axis. Well, in this case, the energy is constant. So this corresponds, if you move to another domain, or if you map infinity to some other boundary point, to a hyperbolic geodesic. So the image of a semicircle. Okay, but of course, for an SLE curve, the energy is going to be infinite, right? Because for Brownian motion, this Dirichlet energy is almost surely infinite. Okay, so we are interested now in understanding something about chords with finite Loebner energy, meaning the driving term, the driving function, has finite Dirichlet energy. Okay, so what sort of curves are they? Well, we know that at least SLE curves are not allowed. And actually these finite energy chords are pretty smooth in the sense that they are always simple. They are locally rectifiable. This was proved by Peter Fritz and Atul Shekhar, working directly with the Loebner equation. But they are not C1. So they can have spirals, not logarithmic spirals, but some kind of slow spirals. But on the other hand, C1 does not imply finite energy either. So I guess many of you probably already anticipated the sort of link to probability, or to SLEs in particular, and it's the following. So of course, the Dirichlet energy, the one-dimensional Dirichlet energy, is the large deviation rate function for Brownian motion. This is a classical result. So if one assumes that this Loebner transform, or this mapping from driving function to curve, is continuous, we get, at least heuristically, the following link to SLE, namely that the probability that an SLE kappa curve stays close in some way to a given chord gamma, then this should, as kappa goes to 0, decay like e to the minus the energy divided by kappa. And this was made precise also in the original paper of Yilin, and recently improved. This, I mean, the question is somehow which topology you put on the curve and how exactly you understand this stays close to. So this was recently improved to Hausdorff distance here, but it will be interesting to try to improve this to stronger topologies also. So at least for me, I think this finite energy chords, they are really the best sort of interpretation of what one should mean by SLE 0+. So some kind of semi-classical limit of SLEs, or some kind of deterministic version of SLEs, if you will. Here, I just want to mention that because this is interesting, I'm not sure how well known this is in the probability community, but there is also another very interesting class of driving function that's also deterministic, where you have the condition that the driving function is Hölder 1/2, with a small semi-norm. So in the modulus of continuity, you have a constant in front of the square root. And if this constant is strictly smaller than 4, it turns out you always get a curve. But these curves actually are sort of geometrically, in some sense, more interesting than these finite energy curves. They can be fractals, and they are phase transitions, and so on. So there's this kind of similarities between the SLE story there as well, but in a deterministic setting. But this goes a bit in a different direction. Okay, so once you have this connection to SLEs, you can start thinking, what can I learn about my finite energy chords? But for those of you who have seen, who know SLE theory, you probably have seen this SLE Green's function, which is the sort of density that tells you a renormalized probability that the curve gets close to a given point. At least heuristically, given such a large deviation result, if you sort of loosely exchange a few limits, you could predict that the minimal energy that is needed for a chord to pass through a given point in the upper half plane is computed like this. That's basically taking a logarithm of the Green's function and then renormalizing and passing to the limit. This can also be proved directly. So this also gives you some intuition. You can also see from this somehow why you cannot allow logarithmic spirals. This would give infinite energy. You can also see why you would not be able to have double points on the curve, and the curve cannot hit the real line, and so on. So for a given energy, you will always stay in a fixed cone, in fact. But I think the sort of first really sort of, I don't know, surprising or remarkable result about these finite energy chords was also due to Yilin. So this says that actually this Loeffler energy is invariant with respect to reversal of the curve. So if you don't know about this connection to SLE, this is super surprising, I think, because the description in terms of the Loeffler equation is somehow very directional. And if you reverse the curve, you flip 0 and infinity, there's no really no relation that we know of, or good relation between the sort of driving functions of these two curves, even though they are related by a very simple transformation. But given the known reversibility of SLEs to Dapeng-Zhan, and given such a result, this can be proved also. Okay, so this is the sort of chordal Loeffler energy, but it's actually a better description that I want to go to now. So here the setting is the following, that I consider not a chord anymore, but a curve sort of sitting in the Riemann sphere passing through infinity. So it's a Jordan curve. And then there is a conformal map from the upper half plane onto, I don't know, one of the sides, let's call it H. And there's another conformal map from the lower half plane mapping to the lower side, and they are both fixing infinity, say. And then actually it's possible to associate or write down a Loeffler energy for this generalization of a chord according to this formula. So the energy is equal to the Dirichlet energy of log absolute value f prime plus the energy of the corresponding quantity for G. Okay, and these are conformal maps. So by Cauchy-Riemann equations, you can also write this in terms of the argument and so on. And actually chords are a special case here, because if you think about the chord as, okay, so it's living in the upper half plane, but if we apply, if we square this, the half plane, the real line gets mapped to the positive real line. And if we think about this CI as now living in the Riemann sphere, it looks like this. So actually this chord is just an example of the situation we had up here, but where part of it is somehow straight. Okay, so if you view this chord like this, it becomes very natural to say, well, let me try to somehow apply maybe Möbius transformation to maybe move this together, and in this way somehow define an energy associated to loops. And this was done by Steffen-Rode and Ian Wang also. Okay. And with this definition of Loeffler energy, which is also was discovered by Yilin also, it turns out actually that these loops with finite learner energy, this class of loops with finite learner energy is actually the same as something called the class of Weil-Peterson quasi-circles. So this class of quasi-circle, or class of Jordan curve, if you want, has been studied both by mathematicians and physicists for a while, actually. There is a monograph by Tatayan and Theo from 2004, and somehow this class was of interest to physicists in some aspects of string theory, and also, for instance, in Mumford's program on theory of shapes within sort of the theory of computer vision and so on. And well, it turns this is also a kind of complicated and developing story, so I won't really go into it. But somehow this learner energy both now characterizes this class, the property to have finite learner energy, but also it turns out that this class of Weil-Peterson quasi-circles, if you view them somehow in the right way, it turns out that there's a lot of geometric structure. So in fact, this carries some sort of infinite dimensional Kähler structure, and this learner energy is in fact very closely related to this this geometric structure. So this one can read about, for instance, in Tatayan and Theo. And there's a recent preprint of Chris Bishop. So this is this sort of diagram on the right here that lists actually 26 different characterizations of Weil-Peterson quasi-circles, both geometric and analytic. And actually some even generalize to higher dimensions. So this is also an interesting developing story. But somehow the point I want to make here is that this connection with random conformal geometry through these large deviation type ideas, this is a new thing, right? So this gives a link between probability to all these different descriptions. And there are many interesting problems, both sort of going from the probabilistic world into this analytic world, try to be inspired by probabilistic symmetries and say nice things about the analytic world, and also vice versa to maybe think about what these structures could mean in the sort of rougher random setting and so on. And I should also say here that this, well, part of our joint work also gives another characterization that Gillian will discuss also. Okay, so let me now switch gears a little bit and discuss the first of our two joint papers. So again, we switch now to this sort of random conformal geometry mode, and we remember, for those of you who have the slides, you can go back a little bit to think about these different coupling theorems in the random world, and we were interested in understanding some things about them from an analytic perspective. Okay, so here's the first theorem. Here's the setup. So I consider a function on the plane with finite Dirichlet energy. And okay, then one can check that it's possible to associate a locally finite measure with such a function. And okay, and I let eta be a Jordan curve through infinity. So in similar way as I had a few slides ago. Then I'm going to do the following. So again, I consider two conformal maps from the upper and lower half planes onto the two parts of the sphere that's determined by my curve eta. And let's assume that they fix infinity, both of them. Then if I look at my phi here, my function with finite in the Dirichlet class, I can look at its restriction to these two sides of the curve. And there's at least if you think about having this sort of measure sitting around, there's a natural sort of transformation law obtained by sort of transplanting these two restrictions of phi onto the upper and lower half planes via these conformal maps f and g in such a way that you get the corresponding measures here just equal the pullbacks of the restrictions up and down. Right? So that is just so u is just by definition phi composed with f plus this log term involving the derivative. Okay, And then the theorem is the following, that the Dirichlet energy of this phi, this guy living on the whole plane, plus the Loebner energy of the curve passing through infinity is actually equal exactly to the Dirichlet energies of these two functions that were transplanted, these two sides, the ones that are living on the upper and lower half planes. And you know, one way to say this is that the Wade-Peterson quasi-circle cuts a phi in the Dirichlet class into two half-plane forms that in a way that preserves the total energy. Okay, and well, so some of the probabilistic interpretation is this quantum surface that is cut by an independent SLE. And so why do I say this? I mean, what is the actual link here? Well, let me just give one slide on a sort of super heuristic argument that could be used to, starting from the probabilistic world, to guess that this result should be true. And well, it goes something like this. So one considers this quantum zipper coupling that I mentioned. So we look at the probability that an SLE kappa loop stays close to this prescribed eta, and that this sort of GFF stays close to this prescribed function. And then assuming this coupling, at least, okay, here I'm ignoring log singularities, etc. But as kappa goes to 0, this guy should behave like the same sort of probability where these you have fields on the upper and lower half planes that are coming from cutting along this SLE curve, or cutting using this SLE curve. Okay, and then expressing this in terms of these large deviation rate functions and independence. So these two are supposed to be independent, and also the SLE and the field is also independent. They are also independent. You would expect that actually, if you take the log, multiply by kappa, then as kappa goes to 0, this quantity should, I mean, the rate functions should add up if they are correspond to independent variables. So you should get the sum of these two, and this should be equal to the sum of those two, which is precisely the identity. So this is a way to somehow very, very roughly guess that such a thing might be true, but the proof uses no probability whatsoever. So this is actually rather simple proof, and uses nothing about the coupling results. Okay, so so now we know that somehow you can use a Wade-Peterson quasi-circle to cut this Dirichlet class element in the whole plane into two an upper and lower half plane parts in a way that preserves the energy. So the question is if you can go in the other direction. So starting with the Dirichlet class functions in the upper and lower half planes, can you somehow find a curve and a phi defined on the whole plane such that this corresponding identity holds, and this phi is gotten from the transformation law like this from the upper and lower half plane. So the answer is that this is possible, and this uses another sort of analytic device that is called conformal welding. So let me briefly describe this. So given a Jordan curve, let's say we normalize it so it goes through 0, 1, and infinity with conformal maps, as I described before. So going from the upper and lower half planes onto these different sides of the curve. Then if I first of all, well, I restrict attention, I restrict my function to just the real line. And so I take f, I go here, and then I sort of go back with g. And so both f and g extend continuously to the closure of the half plane, right? So this is somehow well defined, and this actually defines a homeomorphism of the real line. Okay, so any curve through infinity would generate such a homeomorphism by going back and forth with the conformal maps like this. So the conformal welding problem asks to invert this process, to start with a homeomorphism and find the curve with attached conformal maps such that this formula holds. Okay, and this is also a sort of classical idea in geometric function theory, and but this is also a very interesting story. But let me just say that existence and uniqueness are very difficult in general. So this is somehow not known. Also a little bit similar to the Lerner equation. In fact, the Lerner equation is closely related to this. The classical setting is when this homeomorphism is quasi-symmetric. So this was treated by Berling and Alfors, I guess in the 50s already. And then you can always solve this welding problem, and the welding curve is a quasi-circle. Well, there was recently quite a bit of interest in this the sort of rough setting that would correspond to trying to weld together like SLE curves. SLEs are not quasi-circles; they are less regular, but in some probabilistic sense, they still have this sort of random self-similarity that make them a bit similar to quasi-circles. So this is also a developing story, and there has been some very nice results by Stella Jones, Kupiainen, and Saxman, for instance, and also, of course, Sheffield's results in this direction. Okay, so there's this conformal welding that allows you to somehow glue together a curve given a homeomorphism like this. And this is what we use to invert our process. So starting with U in the Dirichlet class for H and V in the Dirichlet class in the lower half plane, one can take traces on the real line and define and weight just one-dimensional Lebesgue measure by e to these traces, and this defines also a nice measure. So then what we do is we define a homeomorphism that we think about these as measuring lengths along the real line, and we just define a homeomorphism that matches these lengths as you measure from above and below. And then well, the theorem is that we call this isometric welding. And the theorem is that there's a unique solution to the associated normalized welding problem, and the welding curve is a Weil-Petersson quasi-circle through infinity, and phi defined from this transformation law does satisfy this sort of cutting identity that I showed before. Okay, so let me not say so much about the proof. I mean, just to mention one thing that goes into it, and this is this nice characterization of Weil-Petersson quasi-circles through the welding homeomorphism. So this is also a fairly recent result due to Shen, Tan, and Wu that says that you have a Weil-Petersson quasi-circle if and only if log of H prime, so H is this welding homeomorphism, is in H1/2. So it's this fractional Sobolev space. Basically, if this quantity is finite, this sort of integral is finite for log of H prime. And then there's a close relation between H1/2 and the H1/2 norm, semi-norm, and the Dirichlet energy of the Poisson extension of U to the upper half plane. This is also a classical result called Douglas formula. By the way, so this notation I will use later also. So P of U means the Poisson extension of a function so just the harmonic extension of this guy. So this part is somehow not so hard. It requires slightly more work to show that you can somehow glue together that this phi that we get from this transformation law actually is an element of is an element of the Sobolev of the Dirichlet class for the whole plane somehow. So one has to show that this somehow glues together correctly. Okay, right. So so the next results sort of go in the direction of the other sort of coupling results. They're also inspired by that story. So here I just remind that remember that we could write the Lerner energy of our curve in terms of the Dirichlet energy of log of absolute value of f prime plus Dirichlet energy of log absolute value g prime. But this is just the same, of course, as looking at the argument of f prime and the argument of g prime. And this argument of f and g prime can be interpreted geometrically as a sort of winding along the curve. So in some sense, you can think about the Löwner energy as being just the Dirichlet energy of the harmonically extended winding along the curve, interpreted appropriately. Of course, you have to be a little bit careful because it's not a C1 curve and so on. But okay, it has other nice properties that allow one to make this interpretation in a nice way. Okay, so that's the first remark. So then the result is the following. So suppose you have a Dirichlet class function. Here it should just be not C1, but C actually. So we have a continuous such guy with the added assumption that the limit exists at infinity. This is some technical assumption. It's not so important, but then we consider a solution to to this sort of ODE. So we really treat or think about a flow line attached to this this phi, starting from some point in the plane. Then one can check that if you go, well, you let t go back both to negative infinity and plus infinity, this actually produces a curve, or any such solution produces a curve, that a Jordan curve that runs through infinity. And it is actually a Weil-Peterson quasi-circle, and the Dirichlet energy of phi is equal to the Löwner energy of this solution, of this flow line, plus the energy of the zero trace part of phi. So just what we get by looking at phi and then removing the Poisson extension of the restriction of phi to the curve. That's what this means. And here again, I just repeated what I said in the last slide, basically that this Löwner energy can be understood as also the Dirichlet energy of the sort of quote unquote winding along the curve. And again, here I emphasize that the curve is really determined by the function phi, as opposed to our previous results where we could choose any curve and sort of cut our phi into two pieces. Here, the curve is really determined by the field, quote unquote. And the probabilistic interpretation again is that this is a version or sort of deterministic version of the forward SLE-GFF coupling, the flow line coupling. But again, the proof is pretty simple. I mean, it's not and it's purely analytic, so it uses really no connections to probability, except that one guesses that such a thing should be true and then tries to prove it. Okay. Right, so the last result I want to present is the following. So this was something that we didn't really, just came sort of at the end of the paper as a corollary. So there's somehow a way to express rather neatly, I think, these two. So we had both this sort of cutting identity, and we had this flow line identity, and there's a way to somehow express both of them simultaneously. And this is what we call this complex identity does. So here we look at a complex valued function on the plane in the Dirichlet class, such that the imaginary part here satisfies this assumption that I had on the previous slide. It should be continuous with the limit at infinity and so on. And then I let again eta be a flow line of this vector field, but by this actually mean just the flow line corresponding to the imaginary parts. We don't care about the time parameterization here. And so I read this curve from the field or from the psi here, and then I have associated maps, conformal maps, f and g, exactly as before. And then the theorem is that the Dirichlet energy of psi is equal to the sum of the Dirichlet energies of capital U and capital V, where U and V are defined like this. And the proof of this result uses the cutting and the flow line identities, but also given this result, it's easy to see that you also can conclude both the identities that we had before. I mean, for example, by taking phi to be 0, and yeah, the field is just equal to the Poisson extension of psi and so on. And okay, so this is now equivalent to the cutting and flow line identities combined. So okay, so this is even more vague than what I said before, but somehow the probabilistic interpretation of this result is something that we were a bit, I don't know, puzzled by or thought a lot about. And in some sense, it can be viewed as a kind of seed or some kind of facet of analytic facet of this mating of trees story due to Miller-Sheffield, Duplantier, Miller, and Sheffield. And this story continues in Yilin's talk, but this trying to understand this complex identity was really, in many ways, the starting point of the sort of next part of the story, which is what she will explain. Even though we didn't emphasize it so much in the paper. So she will also present a slightly different version of the complex identity. Okay, so let me not discuss it, but also I will just mention that these results that were somehow inspired by probability, but they can also be used to prove new interesting things about, I mean, purely analytic things. That was another actually initial motivation for this project, to think about some question about welding together certain types of welding homeomorphisms and how they behave and so on. Okay, so let me sort of start to round up by presenting this this kind of dictionary that we have in the paper also. And I mean, okay, so there are many lines here, and it's not so important exactly. The point is just that in a sort of fairly vague but still useful way, that is somehow possible to translate a lot of the statements and objects in random conformal geometry to statements and objects in this sort of Wade-Peterson finite energy world. And the somehow advantage on the right hand side is that they are easier to deal with analytically and so on. And we have many sort of, I think, surprising symmetries and relations somehow that would have been difficult to see without being inspired from the probabilistic world. And then in the next hour, you will hear about a sort of continuation of these stories, where here on the left-hand side, we have SLE duality and this mating of trees framework. And on the right-hand side, we have these Wade-Peterson foliations and energy duality. And here also in the end, you will see that we start to also get to where we prove things here that allow us to also make predictions of things that should be true on the left-hand side that aren't proved yet. I mean, most of the stuff we did now was somehow known on the left-hand side, and we prove analytic results that somehow mirror these results, but it's actually now possible to somehow go further here. Okay, so just as a summary, what happened during this first part? Well, I defined some background material from conformal geometry, the SLEs and the GFF. I also defined the Löwner energy for chords and for Jordan curves. That was both sort of dynamically through the Löwner equation and then also statically through this the Riemann maps. And then there was this link that was established by Yilin through that links this Löwner energy through this Wade-Peterson quasi-circles, right? And so we have this interesting connection between two worlds that previously didn't speak so much to each other, and one can try to go back and forth to learn new things. And I gave one example of such a result where we used inspiration from probabilistic models to prove new things about actually really classical objects. I mean, things like the Dirichlet energy and the Dirichlet class, sort of nice symmetries for various objects that were not known before. And I sort of argue that we can interpret our results as some kind of deterministic analogs of SLE-GFF interactions. And well, certainly I feel that this, to some extent, clarifies these probabilistic results, which are not easy results. I mean, these are not easy things to prove, but somehow these analytic arguments are pretty short, and once you have the right setup, rather simple in some sense at least. So this somehow clarifies the analytic content of these coupling results, and depending on your point of view, I suppose, but quote unquote explains probabilistic symmetries. Right, but again, proofs are purely analytic and rather short. So I think I'm out of time. So thanks a lot for listening. Sorry for running over, actually. Yeah, thanks.
Okay, thank you very much. I'll just invite everyone to unmute themselves, and then we can all thank Fredrik. So, does anyone have any questions? So if you'd like to ask a question, there's several ways of doing it. Either you can raise your hand and I'll invite you to ask your question, or you can type it in the chat and I'll relay it to Fredrik. Alessandra, yeah.
Yes, I have a question. So what is the connection with the computer vision? You mentioned that these Weil-Peterson quasi-circles were studied for computer vision.
So that's a good question. So there is there's some work, as I mentioned, by Mumford and various collaborators. So they are somehow trying to, there's one question, how do you, if you have a shape, how should you encode this in a useful way? And so if you have a two-dimensional shape, one approach to this is through this, if you trace the sort of outer boundary, if this is a Jordan curve, then you have this homeomorphism, this welding homeomorphism, right? And so this was their approach somehow to encode, try to think about how to use this in a sort of computer vision context when you encode a shape through the homeomorphism. And then somehow, because there are nice properties, nice ways to deform within this Weil-Peterson class, it's, this is a good class to work with, and there are somehow nice ways to measure distances and so on, and so this can somehow be used to try to understand, how do you measure a distance between different shapes and so on. So I think this is maybe Elin can want to add something, but this is some rough link. I think this is not a story which is at all completely developed in some sense, right? So I think there are still people thinking about this.
Okay, thanks.
Okay, there's been a question in the chat. I know Yelin sort of tried to answer it a bit, but maybe you want to sort of comment a bit. So just asking sort of what exactly is a Weil-Peterson quasi-circle?
What exactly is it? Well, right. So that's a good question. I can give you 27 different definitions, characterizations, but no, I mean, I think maybe the best, cleanest definition for us now would be to say that this is a Jordan curve through that passes through infinity, and then you look at these conformal maps from the upper and lower half planes fixing infinity. So such a Jordan curve is a Weil-Peterson quasi-circle if and only if the Dirichlet energy of log of f prime plus the Dirichlet energy of log of g prime is finite. And actually, it's enough that just one of them is finite if you have a Jordan curve. So this is another equivalent definition is that the welding homeomorphism satisfies that log of h prime is an h1/2, and there are the more, I guess, classical definition would be that it's the closure of you look at this welding homomorphisms that are smooth, and then but this I don't want to get into details, but there's this particular metric you can put on sort of from the point of view of Teichmüller theory, and you can take a closure in this particular metric and what the sort of curves that you get that correspond to these sort of limiting homeomorphisms are also the Weil-Peterson quasi-circles. So there are a bunch of different characterizations, both analytic and and geometric, but I think for me this one is maybe the most useful one, perhaps. Yeah, I don't know if this answers this. It's a but one thing that is maybe I could mention is that so in this paper of Bishop, I mean, there was an open problem to give a purely geometric characterization of such quasi-circles, and that was open until his paper somehow. And he has several different geometric ones. By geometric, I mean not things involving the conformal map, for instance. Yeah.
Okay, thank you. I have a quick question if no one else has anything to ask right now, which is you talk a lot about this analog between your approach and imagined geometry. Is there, I mean, is it just an analog, or is there some hope that you can somehow establish a one-to-one connection between results in imagined geometry and results in your framework?
I mean, I think that is one could certainly try to. So I gave this sort of heuristic derivation from the point of view of large deviations, and I mean, I suppose in principle you could prove, for these couplings, you try to prove some precise large deviation type results that would involve, and then our results would be statements about the rate functions essentially, yeah, that is. That is probably doable somehow, but with a lot of work, especially I mean, especially with things involving the welding story, for example. I mean, this is also not well understood from the analytical perspective. If you change a little bit your welding homeomorphism, how is the curve changing, and these sorts of things are quite tricky to answer. But yeah.
Okay, thank you. I think we're just about out of time for questions. So again, if I'll just ask everyone to unmute themselves once more, and we can thank Frederick once more. And then I suggest we take a 5-minute break just so people can go and grab a cup of coffee, and we'll start again at 5 past the hour with Jelen's talk.
If you want to share your screen, it's up to you.
Yeah, I can share. You can see it?
Yes, it's okay. Thanks.
Yeah.
Okay, I think it's time to start again. Just an announcement before. So I recall you that next week we will have the talks of Matthias Erbar and Jan Maas. So it's a pleasure now to have here Jillian Wang. She will continue to talk about the interplay between Dirichlet and lunar energies. Thanks.
Thank you very much for the invitation, and also thanks a lot to Frederick for the nice introduction and advertisement. I will continue talking about the interplay between Dirichlet and lunar energies we're going to see a lot of Weil-Petersson quality circles, SLEs as well. But I will try to make this talk as self-contained as possible. Just a repeat from Frederick's talk that's about the motivation, how we get this story started, was that in the previous joint work with Frederick, we have found there are welding identities and flow line identities between Lovener energy, which is defined for a Jordan curve, and the Dirichlet energy for functions which lives on the complex plane. There's some nice interplay. They're inspired by results from random conformal geometry, although the proof doesn't go through random conformal geometry, but there are very close analogs between them. And the intriguing part of that is that this welding identity and flow line identities, they seem to be quite different, where in welding identity, the curve is totally independent with the field. And in the flow line identity, the curve is determined by the field. But however, they can be expressed together into one complex identity that, so we started to ask ourselves, what is this complex identity is really saying, and what is stochastic analog of that? So the answer that we came up to is that there is about the mating of trees theorem. This is a result by Dubonte Miller Sheffield, which actually also put together this quantum zipper and imaginary geometry. And roughly speaking, this is, if you go to one of those talks, you can probably see Scott doing this motion of like having two trees, they intertwine together to form a Riemann sphere. And what are these trees? There will be two pairs of trees. Each of them, they're having branch being like SLE curves. And they're actually flow lines of underlying Gaussian phi field. And in the middle tree story, there's also another Gaussian phi field, which gives a Liouville quantum gravity that is independent with those trees. There's a Liouville quantum gravity that is underlying, is putting on the sphere. And so that actually corresponds to our complex identity. So the Liouville quantum gravity that will correspond to the exponential to the 2 times the real part of a complex field. And this is giving you a measure in the finite energy world, as in the random conformal geometry, that's a random measure on the Riemann sphere. And the trees, they're filling they're space filling, and so the branch of the trees actually encodes the information about some winding field, and that is corresponding to the imaginary part of our complex field. But there's a third player in this story, that is space filling SLE 16 over kappa curve. So those trees, if you take a very small kappa, those trees are having branches there for, they're fractal branches, but they're not super fractal. It's a, let's say, Hausdorff dimension 1 plus 8 over kappa. Sorry, kappa over 8. And there's actually, you can trace the curve that in between these two curves, and there will be a SLE 16 over kappa curve. And now for small, very small kappa, the 16 over kappa is very large. And then we ask the question, what is the finite energy analog about this space filling SLE kappa curve, 16 over kappa curve? And I use this slide as the introduction, is that if we just want to study this large kappa SLE curve and its large deviation, we thought about the SLE duality. What this says is that if you draw a space filling SLE kappa, but when kappa is greater than 8, this is almost surely a space filling random curve, and which is drawn in orange. Here, this is, if I stop it at some time, and if I look at the outer boundary of this cluster, it's SLE kappa 16 over kappa curve. So here now kappa is large, and so this number is small. It says that if we understand the asymptotic behavior of SLE 0 plus, which is giving you the Loeffner energy from the Schroeder theorem, where the large deviation of Brownian motion, etc., then there should be a dual story about SLE infinity when kappa goes to infinity. And the first part of my talk is to really understand this large deviation of SLE infinity. And this is a joint work with 2 graduate students at MIT, Ming-Jae Park and Maurice Ang. And the large deviation rate function, they're called the Loeffner-Kufarev energy that I will define it shortly. And the second part of my talk is to really see how the Loeffner energy itself for Weil-Petersson quasi-circles, and how is that dual to this Loeffner-Kufarev energy. That's the plan. And just to remind that what is the link, what is Weil-Petersson quasi-circle, and thanks also for the question in the chat. So we say that a gamma is a Weil-Petersson quasi-circle if the conformal map from inside disk to inside of curve gamma is log of f prime. This is conformal map to f, log of f prime has finite Dirichlet energy. If it is this quantity is finite, then we call this is a Weil-Petersson quasi-circle. And a theorem that I proved before was that also Frederick stated is that the Loeffner energy is finite if and only if gamma is a Weil-Petersson quasi-circle. And moreover, you have this identity, the right hand, the Loeffner energy of gamma equals to this formula here. I just want to emphasize it's a quite remarkable result, because on the left-hand side, this is defined as the Dirichlet energy of a driving function, which comes from Loeffner transform, that where you have to consider a lot of conformal maps at the same time in order to tell what is the driving function of this loop, and then take the Dirichlet energy about that. It's quite complicated, hard to compute. But on the right-hand side, you only need to consider 2 conformal maps. And so this is, I call this a dynamic definition for Loeffner energy, but on the right-hand side, it's just a static definition. So if you don't remember about what is driving function, never mind, just you can think the right-hand side as a definition of being the Loeffner energy of gamma. And those Weil-Petersson quasi-circles have attracted a lot of attention, started by people doing string theory. So circles they like because they are closed string, and especially they're interested in geometric structure, Kähler structure, the space of loops. And all this work in the 80s and the 90s by both physicists and mathematicians. They concern the smooth part of curves. And there are smooth diffeomorphism on the circle as welding homomorphism. And it's really starting from the 21st century, especially work with Cui. Cui has probably the first person studied what is the completion about this smooth part, but his work has not been recognized, also not known. At least Tata Hong Teo didn't know Cui's work before. But then Tata Hong Teo, in their memo of AMS, they really studied this class of a Peterson quasi-circle systematically. And those work are concerns really the completion about those loose curves. And also works by Shentang Wu and the recent preprint of Bishop. And they're related to conformal field theory as this using the Peterson quasi-circle as one of the key tools in giving one definition of conformal field theory. This is approach by Ratnell, Schipper, Staubach. And by Sharon Mumford, they used the Peterson metric on those quasi-circles, study computer vision, and studying geodesics in this infinite dimensional space of loops. They led to studies of periodic KdV equations. So also contributing to that like KdV equation story. And also it's related to a so-called holographic principle that has been studied by Bishop, but this is a principle that theoretical physicists has been looking at a lot. What they say is that I have my curve living on the Riemann sphere. So the Riemann sphere is it has a conformal, sorry, I hear some echo. No?
Oh, it's okay.
Yeah. The Riemann sphere has its automorphism group as a Möbius transformation. And those automorphism, each conformal map of the Riemann sphere to itself extend to isometry in hyperbolic three space. You just imagine that you fill your Riemann sphere inside by a three-dimensional hyperbolic ball. And it's very natural to characterize those Peterson quasi-circle living on the boundary of this hyperbolic three space by something that is related to quantity inside the hyperbolic three space. And this is saying that information on the boundary can be read by things in the bulk and vice versa. This is called holographic principle. And in Bishop's recent work, he related those Peterson quasi-circle to be exactly those curves which can be the boundary of a minimal surface in this hyperbolic three space with finite total curvature. And it's also if and only if characterization. So that actually don't understand very much now, but it will lead to many, I'm sure that it's going to lead to a lot of open questions later on. And also, as you heard from Frederick's talk, that now this Peterson quasi-circle, they're related to random conformal geometry as being the curve with finite Lovener energy, the large deviation rate function of SLE as with finite. All right. And again, this is a list of Bishop's. There are some of new results from him, and some are very known early on, but I will just skip. So, but the focus of my talk is to talk about this additional characterization about the Peterson quasi-circle, and that is inspired by the SLE duality. Okay. So to describe our results, I will need this version of Lovener equation. The setup is we start with a family of measures. So this n plus, this denotes processes of measures where each of the rho t is a probability measure on the circle. And we only assume this dependence on t is measurable. And this would be called the driving measure. The Lovener-Kovarev equation, I'm looking at the version where we target at the interior point. So in fact, there's some technical issue that we can't take the caudal one as Frederick described, but this radial one actually makes everything cleaner. And how is this measure is encoded into this equation? You don't really have to read it, but essentially it's solving a differential equations starting from the identity map. And as time evolves, this conformal map, it will give you, it is a map from the unit disk to some subdomain of the unit disk containing 0. And its derivative at 0 is exponential minus t. This is saying that this dt has conformal radius, just exponential minus t. And the intuition about the relation of rho and the ft is that if rho is regular enough, if rho has a density, say I have the normal velocity of the boundary of dt is given by this 2 pi rho, but times the derivative of a conformal map to the first power. So if the rho doesn't have to be supported on the whole circle, it can be 0 at any place, and that will be the place where the interface don't move. And where this is positive, your domain will be pushed inside. And the normalization, such that they're all probability measures, it ensures that this conformal radius decays like exponential minus t. So the upshot is that if I'm given a family of measures, probability measure on the circle, it gives me a family of conformal maps, ft. They're mapping onto the evolution family dt. And this family of dt, they're always shrinking. All right. And these are equivalent. Either way, you can determine the evolution family by ft, and you can determine that. So these three terms can be determined one after the other, one by the other. We will be rather looking at this viewpoint. If I'm giving you a family of measure, I will look at the evolution family of dt. Let's start with example. The simple one, if we take the measure to be uniform, you're pushing inside uniformly everywhere from the circle. What you obtain, they are concentric disks. If you take your measure, it's another extreme, and this is not absolutely continuous with respect to Lebesgue measure. It's direct mass, a direct measure, but at a random place, which is following Brownian motions on the circle, which is just exponential I times the Brownian motion. I'm going to choose the variance of the Brownian motion, this kappa. I put kappa here, so that the larger the kappa is, the faster this driving measure moves on the circle. And this gives me the radial SLE kappa. All right, this has the same phase transition as the caudal case. When kappa less than 4, you get the simple curve with the targeting at 0. And kappa between 4 and 8, it will bouncing on each other, and the shrinking domain is colored in yellow. The shrinking domain is the yellow part. And when kappa is larger than 8, it's space filling, and it can wrap around. All this, in this case, it can also wrap around. So already looking at this picture, and now we are going towards when kappa goes to infinity, and to see what happened. All right, if kappa moves really, really fast, it's going to not distinguish any point on the circle. But immediately after no time, you will move from this point to this point, and you can start your Brownian motion start here. By strong Markov property, I have my Brownian motion starting from here, or Brownian motion starting from here. It's exactly the same. All right, so it shouldn't be surprising that when kappa, also from ergodic theorem, for instance, that when kappa goes to infinity, this measure, viewed as a measure on the cylinder, where the cylinder is indexed by t and theta, it will converge to this uniform measure. So if I just draw this picture here, this is time, this is the circle, and if I draw my Brownian motion by this red, is moving on the circle, and as time evolves, it moves up. And when kappa goes to infinity, it's going to spread out over the cylinder. And this measure, as a measure on the cylinder, converges weakly to this uniform measure. It's still a measure which has probability as marginals. So this is the probability measure on the circle. So there's a very natural topology that one can put on the evolution family of domain D, such that this map from the driving measure towards the evolution of domain is a homeomorphism. So everything that you look at on the driving measure, it transfers nicely towards the topology of the evolution of domain. And just from the heuristic that I described, that we obtain is that when kappa goes to infinity, this evolution family of SLE kappa domains converges to this trivial picture of shrinking domain. Also, the large deviation depends on topology, but because of this nice homeomorphism between the measure and the evolution family, and we just studied the large deviation of the driving measure. And what we obtain is that the radial SLE process satisfies the large deviation principle as kappa goes to infinity with rate function, a certain measure that's defined here. Let me just say, what is this large deviation as kappa goes to infinity means? It means heuristically that the probability of SLE kappa domains, the complement of SLE house, stay close to evolution family D, deterministic, anything we choose. It decays when kappa goes to infinity as the exponential of minus kappa times this Viklund-Kufarev energy. And this is what this large deviation when kappa goes to infinity, it means. And this definition of the Viklund-Kufarev energy is defined by an integral of L of rho t, where L of rho t is defined as 1/2 of the Dirichlet energy of the square root of the density of rho t. If I write rho t as the mu t squared, d theta L rho t is the Dirichlet energy of nu t. So already here, you can see that for L of rho t to be finite, rho t has to be quite regular. It has to be absolutely continuous with respect to Lebesgue measure. All the Dirac measures, they are ruled out. And moreover, not only has the density, but the density itself is square of some W12 function, some guy with finite Dirichlet energy. And we just set this L of rho t to be infinite if it's not the case. Right, so this large deviation is quite different than the kappa goes to 0 large deviation. So for when kappa goes to 0, if we do the large deviation for Brownian motion, it more or less follows from the Kramer-Martin theorem, where if you shift your Brownian motion by a function with finite Dirichlet energy, then you have the density, your original measure and the image measure is absolutely continuous with respect to each other. But here, this large deviation is very different. It's completely changing the nature. If you add your Brownian motion by a measure with finite Viklund-Kufarev energy, it's not anymore a family of, it's not absolutely continuous with the original measure. So just to say this is quite different than the kappa goes to 0. But the way we prove this is again by this picture. So the idea is that because we are looking at the measure, if I stop at a certain time and I look at what is the measure on this small time slice, then what is the Brownian motion? If I project that to the circle, it is going to give me the occupation measure of the Brownian motion. And we can look at kappa goes to infinity, how this occupation measure behaves when, what is its large deviation. that instead of studying, so this is the study of occupation measure, then we pass that to the process of occupation measure by strong Markov property, actually, weak Markov property, no. And that uses a result by Varadon and Danske, which gives you this term, this L of rho t is actually the Lorentz deviation for a Brownian occupation measure. And now as a process, we just integrate this. All right. So this is the first part of my talk, that is describing what is the Lorentz deviation when kappa goes to infinity of SLE. In the second part of my talk is that we are going to try to understand what is, in which sense this Lovener-Kovarev energy is dual to the Lovener energy. And before doing that, I would like to introduce a more symmetric version of Lovener-Kovarev chain. So that is the whole plane Lovener-Kovarev chain. It's very similar to the radial case. The only difference is now the time is indexed also by negative t, and it gives you a evolution family, shrinking family of domains dt, where t is again indexed by dt, all the real numbers. And you have also a family of ft from unit disk to dt with the same normalization. So when t is negative, this conformal radius is larger than 1. And the picture you obtain is actually a shrinking domain which coming from infinity and shrinks towards 0. And circle is not anymore a special place. And how to define it is that if I just stop at a certain time ds, this is a family such that if I map this inside towards the unit disk, then all the other curves that's inside, these are the boundaries of dt's, and they will be given by this Lovener-Kovarev chain and generated by the measure starting from time s. So if you don't like it, you can also think just in the case of the disk, but complete your picture by concentric circle outside. This is one example of a whole plane Lovener-Kovarev chain where all the measure for negative time is uniform. And we define the Lovener-Kovarev energy for this type of measure again as the integral of L of rho t. All right, in this whole plane setup, the result I proved first was the first result I proved with Friedrich is that this qualitative description about the Lovener chain driven by finite Lovener-Kovarev energy measure. So if this measure is finite, then all the boundary of this domain dt is a Weil-Petersen quasi-circle. No exception, or t. The second thing is that the union of dt is the whole plane minus the target point. And moreover, it moves in a continuous manner. This is what we call the foliation by the Peterson quasi-circles. Foliation might not be a good name because in geometry, foliation probably refer to where the leaves are smooth and they're injective, they keep moving towards one direction. But here in our case, the Peterson quasi-circle, they can stay unchanged for some place and grow only from the other place. So this is still allowed. And that's why we put the foliation quote mark. All right, so this is already showing you some duality. That Weil-Petersen quasi-circle, those are exactly the curves with finite Lovener energy. And now it arises naturally from this evolution of measures with finite Lovener-Kovarev energy. And then we're going to describe this in a more quantitative way by associating to a foliation a Wang function. Right? This picture is probably a bit misleading because actually you can also have a curve which is not changing, moving anytime. But the Wang function actually doesn't matter to define it. So the winding function is defined by this, where gt is the inverse of ft and its argument of gt prime z over gt z. It's a formula, doesn't matter. But geometrically, what this means is that this is, if its value at the point z is given by the angle between the tangent of this curve passing through z and the angle with the circle which is centered at 0 passing through z. So this is the angle which is given by this number phi of z. And why I say if two leaves passing through the same point, it doesn't matter, because for the monotonicity, if the tangent exists, then the tangent have to match. And because of this geometric definition, it doesn't matter which leaf that you take. This is purely geometric. Our quantitative result is saying that 16 times of Lovener-Kovarev energy equals to the Dirichlet energy of this winding function. Again, on the left-hand side, this is a dynamic definition. A family of measures, you have to generate dynamically the whole bunch of domains. And on the right-hand side is a static. You just look at how this foliation is like, write down its Dirichlet energy. And they're equal. And our result actually says that one is finite if and only if the other is finite. So this is really the optimal result that we can hope for. And this number 16, so by the way, the choice of this 1 over pi of the Dirichlet energy is such that in the definition of Lovener energy, there's no factor in front of Dirichlet energy. In my first slides where I show that the Lovener energy can be written as Dirichlet energy of some log f prime, is the same Dirichlet energy here. So on the right-hand side, somehow it's related to the large deviation of SLE small kappa, and on the right-hand side, small kappa, on the left-hand side, large kappa. This 16 is consistent with the SLE duality, this 16 over kappa. All right, this is our mean result. And this result has a lot of consequence. Some of them are actually surprising. But before that, let's see an example. So this is an example of a measure which is not positive all the time. So it takes value sine squared theta over 2 for t belonging to 0 and 1. So it takes 0 value at this point, and all positive elsewhere. And we decide to take the uniform measure for other t's. And on the left-hand side, this is the foliation that you obtain. These are all circles, actually tangent at this point that obtained here. And once after time 1, you get uniform measures. So actually they're just the equipotentials viewed from this 0 point. They're just image of concentric circle by a conformal map towards this domain. On the right-hand side, this is a picture of the winding function. I believe the winding function is negative here and positive here, or vice versa. Like already in this case, actually, it's not that easy to check that you have this identity hold, because if you just compute this Dirichlet energy, the gradient of phi is actually having a singularity at this point. But this is doable. This is the first example actually we checked for our identity, just to illustrate how it looks like. All right. Our mean result has the first application is called energy reversibility. It's a one-line theorem and a one-line proof. I have a foliation generated by rho. I assume that rho has finite Lovener-Kovarev energy. They're all Weil-Petersson quality circles. It associates to a winding function coming from the angles and etc. And if I apply 1 over z to it, and now these blue curves are inside, the orange curves are outside, I have another foliation, other winding function, and also another measure which generates it. there's no easy relation between rho and rho tilde. But however, their Lovener-Kovarev energy are the same. Why is that? Because if one look at this map 1 over Z, first of all, it preserves all the purple circles, the invert circles centered at 0 to circles centered at 0. 1 over Z is conformal, so it preserves the angles. So what we obtain is that the angles are preserved and the winding functions are preserved, because more specifically the phi tilde equals to phi composed of 1 over Z. And the Dirichlet energy is invariant under conformal maps. So the Dirichlet energy of the winding function, they're the same. Because the energy duality, we have the Lovener-Kovarev energy of rho and rho tilde are they're the same. Well, okay, so looks pretty easy. But unlike the reversibility for Lovener energy for small kappa, so the small kappa large deviation of SLE, that there we can guess that energy reversibility from SLE reversibility. The Lovener energy yeah, but here actually we don't know that if the SLE for large kappa is reversible. This is not known. Somehow this result actually suggests that actually the very large kappa SLE, more specifically that is the whole plane SLE version, whole plane SLE kappa, if you know what that means, is reversible. So this is not known. So if someone interested in proving it, at least it's suggested in the large deviation regime, they have the same large deviation rate function. This is the first consequence. The second consequence is that if we know that if a finite energy measure generates leaves of finite energy Lovener curve, finite Lovener energy curves, the converse is also true. If I'm starting with a curve with finite Lovener energy surrounding 0, I can actually embed it into a foliation such that the generating measure has finite Lovener-Kovarev energy. How to do this? It is one canonical choice of how to complete this foliation is by equipotentials. I take equipotential, by that I mean they're the image of the concentric circle by this conformal map. For the inside orange curve, they're imaged by F, and the blue curve are coming from the circles outside by G. They're all analytic, very nice curves. And we can write down its measure, which generates this foliation. I call it rho gamma. So the special property about this foliation is that the winding functions are actually harmonic inside. The winding function on gamma that is determined by the angle, by the geometry of gamma, but inside, because they're coming from these conformal maps, the winding functions are actually harmonic. And this is a canonical choice because the harmonic functions minimizes the Dirichlet energy for a given boundary value. So that's why we prefer this one. And because this is harmonic, this winding function is a function of log of F prime, which then relates to the Lovener energy. So the result that we obtain is that the Lovener-Kovarev energy of this rho gamma multiplied by 16 equals exactly to the Lovener energy of gamma plus some normalization point. These are two special points, 0 and infinity, and we keep them in F prime G prime here. Okay, a few remarks is that this quantity is always non-negative, so this term is always larger than the Lovener energy itself. And the other thing is that this term is necessary. This is identity because, of course, this is necessary, but one can also see it because from the fact that the Lovener energy is 0 if and only if gamma is a circle, but on the left-hand side, the Lovener-Kovarev energy is 0 if and only if it's a circle centered at 0. So it has to center at 0. That's why there's this correcting terms here. And it's always nice to have an identity than inequality. for me at least. It led to the definition 27 of a curve to be a Peterson quasi-circle, is that if and only if it can be realized as a leaf in the foliation generated by a measure with finite Lovener-Kovarev energy. And moreover, you have the Lovener energy is bounded by 16 times of this optimal foliation, which is giving you harmonic winding function outside of the curve, whose energy is also smaller than any other measure rho generating gamma as a leaf. So, or we can state it this way: if I start with a finite energy rho, then it gives me an uncountable family of curves which foliates the complex plane, and all those leaves, their Lovener energy is uniformly bounded by 16 times the Lovener-Kovarev energy. All right, and it's a very easy way to generate finite Lovener energy curve, even with a good control on what is the Lovener energy. Another consequence is the complex identity in the case of bounded curve. In Frederick's talk, he showed one for infinite curve where this complex identity is expressing simultaneously the welding identity and flow line identity in a mysterious way. And here we have something similar. And it states the transformation law is a bit different. It's log of f prime z over f, and h is the conformal map from outside here. And but the statement is that if you start with complex field, and here complex field is here, has real part, imaginary part, and if I transform that into a complex field inside the disk and outside of the disk using this transformation law, then their Dirichlet energy are preserved. And this Dirichlet energy is the Dirichlet energy of the real part plus the Dirichlet energy and the imaginary part. And to understand what this transformation law it really means is that.
Sorry, I have a question. Could you explain the relation between gamma and psi?
Oh, sorry. Yes. Yeah. Sorry, I should have said that. Being compatible with the imaginary part of it. See, I should have said that. Yeah, gamma is a Peterson quasi-circle compatible with the imaginary part of C if gamma, its winding function along gamma coincides with the imaginary part of C.
Okay, thanks.
This is, yeah, I should have said that. Yeah. It's the same as in Frederick's talk that the flow line is a flow line with the imaginary part of the field. This is a kind of other type of flow line. Maybe a better way to view this is in this picture. Let me just put this part together. We can interpret here this Z and FC is very tempting to like project this complex plane into the cylinder where 0 is sent to this end, infinity sends to this end. And what the zero complex field would mean, it would mean this is a cylinder equipped with the Euclidean metric on the cylinder, the usual one, that's a dz, so the Euclidean area measure. But also decorated with a vector field, which is, the 0 will be the vector field which goes along those purple lines. This is the 0 vector field. And now if I can pull back by F and H, the measure transforms with the factor depending on F prime. And the vector field will move together with F by the conformal map, the argument of F. And this transformation law actually describes how this pair of measure and vector field changes under conformal map. And the theorem says that if I cut my domain with a field that is compatible with the curve, then their Dirichlet energy will be preserved. So it's just a way to interpret what is this log f prime z over fc log of h prime z over h means. We can also separate this into the real part and imaginary part. Real part tells you how the metric moves. It's not only f prime because there was an underlying reference metric on the cylinder. If you project on the complex plane, there will be log z. That's already a factor which stays there. Yeah, so we'll be very interested in, so all these stories started inspired by mating of trees story, where you have a Liouville quantum gravity and also winding field, which give you the branches of the trees. And here the setup is a little bit different because we are using this radial version of Loeffner chain. It's not exactly the same setup than the mating of trees. So I don't want to claim that this is the complex entity is the one corresponding to the mating of trees, but it actually suggests there might be a similar mating of trees version for this radial space filling SLE setup. So this is a parenthesis. It's probably not the, if you haven't seen that, it's probably not very illuminating. I don't have much time. Maybe let me just talk about the proof sketch. Maybe not. Maybe I will just skip to the open questions. No. Something I already mentioned that there should be a stochastic counterpart of the mating of trees, radial mating of trees that we don't know. So our results somehow suggested how one can guess about what is stochastic mating of trees theorem. And the second question is about the reversibility of the whole plane radial SLE kappa for kappa greater than 8. This is not known, but it's suggested by our energy reversibility. And the last question that is kind of opening up, I think it's now it's a purely dream. Maybe for expert in geometric analysis, it will be not too hard, is that from Bishop's work that this curve on the complex plane is Weil-Petersson if and only if it's bound the minimal surface in H3 with finite total curvature. By total curvature, I mean this the determinant of the second fundamental form integrated on the surface with respect to the metric in the hyperbolic 3 space. One example is that if you have a circle which is zero energy curve, if you have a circle, then the minimal surface bounded by this curve, there's only one in this case. That is the hemisphere in the hyperbolic. It's a plane in the hyperbolic 3 space, and it has a zero curvature. And so this total curvature is 0. And in a general case, if you just have a Jordan curve, it's by Anderson that it shows that there's always a minimal surface bounding this curve. But it's not known that for what curve, it was not known for what curve you can get the surface with finite total curvature. And this is shown by Bishop that it's finite total curvature if and only if this curve is Weil-Petersson. Very interesting. And now, in our case, we get this foliation of Weil-Petersson quasi-circle. Then it's very natural you can look at what are the surface about all of those curves. And what is not known also is that if you're given a curve, how many minimal surface are there? In the case of circle, this is a trivial case. There's only one. There are some results about if you have some constraint, if the curve is round enough, in the sense that this is, if the quasi-conformal constant of the circle is very small, then you can get the uniqueness of a minimal surface. And this is the case if the energy is small enough. If the energy is small enough, we know that there's only one minimal surface above it. And then you can look at the whole bunch of family of minimal surface above it, and it's going to give you some, maybe it's going to give you a foliation of the H3, or sometimes you may have a gap that your two surfaces, they're going to leave a room between them, not going to cover it, and one can study how the foliation is. And also notice that on the boundary, we allow the curve to touch each other. They're monotone, but they can merge at some point. But it seems that if you look at the minimal surface above, they will be disjoint. But nothing, what I said is proved, but it gives a lot of interesting things to study, and a lot of theory in hyperbolic free space. Also, we can ask about what is the probabilistic version of that. This is a completely unknown. So yeah, this is the last slide, and second last is just summarizing my talk that for small kappa gives rise to Weil-Petersson quasi-circles and Löfner energy. And the large kappa, it gives Löfner-Kufarov energy. They're dual to each other by SLE duality. And on the right-hand side, we have also this duality of energies by foliation of Weil-Petersson quasi-circle. They're all related to coupled to Gaussian field, whose large deviation is Dirichlet energy, and they're all related together. So this is summarized. And if you're interested in reading that, all this as large deviation of Löfner energy, large deviation of SLE, I recently wrote a survey paper just on arXiv, and you can read that. It's a lecture note. And all the results I described in this talk is in this paper joint with Frederick and with Morris and Ming-Jae, are these two. And from Frederick's talk, if you're interested, these are the first GAFA paper about the welding flow line interplay. And this paper is the one describing the relation between Löfner energy and the Weil-Petersson quasi-circle, the first time where it is proved. And yeah, that's it. Thank you for your attention.
So thanks a lot. So first of all, I would ask to all participants to unmute themselves so that we can all together thank Gilles and also Frederick for their talks. Okay, Gilles first. Okay, thanks. So we have some minutes for questions. So I have a question. So yeah. you have this mapping from rho T, so this family of measures, to the shrinking domains dt. But so the case where T varies, so it's also negative. Is it an extension of the case of a non-negative T, or is something different?
It's a generalization. So if you take the case where, let me see, this is the picture. So if you take the measure to be uniform for all negative T, then the picture you obtain is the one that is the one from the disk. Inside for positive T, you get those domains, like on the right like here. But outside, they will be just concentric circles. So that is the, so if we just look at the positive one, you obtain what is inside, but the negative one, they're given by a concentric circle. So the case of the disk case is somehow a special case of this whole plane version.
Okay. Okay.
Yeah, we can, this is a special, that corresponds to one to be having zero energy for negative time. Zero energy corresponds to uniform measure.
Okay. So is there some other question, any other question?
Maybe I can ask a question if there, so do you need your measures, maybe you already said this and I missed it, do you need your measures rho T to be absolutely continuous on the circle?
No. To prove this, so if it's not absolute continuous, then this energy will be infinite. So what we have in this theorem, that what we actually assume that this we get the foliation. The foliation, by that I mean it's a family of chordal curves, and actually that is in order to define this phi, that chordal curves, they're having tangent almost everywhere, and there's some technicality by considering this quantity. And once you can define this quantity, we didn't start with any assumption on rho, but we have that if this if the direction energy is finite, then we obtain that this guy is finite, which implies that for almost every t, that this is absolute continuous with respect to the circle.
So if you end up with the level energy being infinite, then you don't get so much information. That's the problem with it, I guess. So it means you can get much more information when it's absolutely continuous.
Yeah, right. So if it's not absolutely continuous, then you probably at least from this theorem you don't get much. But there's one thing that might still work. Actually, it's in part of the proof that I didn't present. I can use 1 minute to describe what that is that, so the whole Lovener theory is a very nice tool to study conformally invariant system. As like if you're exploring the domain little by little, and the Dirichlet energy itself is conformally invariant, so we can explore the Lovener chain by peeling this field little by little. So there's one result that we obtained is that there is a very nice bijective isometry that we obtain that we start with finite Dirichlet energy function. Not much assumption on rho here. You can take rho to be direct measures in the. There's some assumption on it, but quite weak, that we can get a map to the cylinder, to the L2 function on the cylinder. By this explicit form, and which is essentially the zero. If you look at the field, you can decompose the field inside the domain D, dt to be its harmonic part and zero trace part. The zero trace part, and this function iota is the normal derivative of the zero trace part if I push to the circle, and this is a function defined on the circle. For each t, that is a function defined on the circle. And so some of the tools in our proof, it goes to some weaker rho, but then the energy, if you start with, so for the 1D function itself, that if we talk about 1D function, then it imposes some regularity on rho because the boundary has to be having a winding, for instance. And by the way, this is a very nice result that I liked a lot also, is that it's this peeling of the Dirichlet function into a function into L2 is having inverse operator. You can actually reconstruct this Dirichlet function by integrating a family of harmonic functions inside dt. And those harmonic functions determined by the function on the cylinder is like if you have a cake that at different level, you're going to cut it in a harmonic way, but it cut into harmonic layers. And this is the map from the cake to layers. And this is piling those layers back to obtain the Dirichlet energy. So this is the result that works in more general for rho. But then when we want to establish this result, we need some assumption on rho so that the terms integrate very into this.
Okay, there are also 2 questions in the chat. So the first one, if you can recall the difference between S rho and S rho gamma.
S rho is an arbitrary measure rho. Oh, maybe you mean this picture. Rho gamma is the rho corresponding to this special foliation. is determined by gamma and the filling with the equipotentials. And the rho is an arbitrary measure which having gamma as a leaf. And so inside there can be other things.
Okay.
Thank you.
So we had also the feedback. So the second question is the following: is the foliation procedure valid for any Weil-Peterson quasi-circle of the 16 in the Bishop paper?
What is of the 16? They're all equivalent in Bishop's paper.
Okay, anyway, is the foliation procedure valid for any Weil-Peterson quasi-circle?
Maybe can you elaborate the question?
Maybe so. Could you clarify the question? Andrei, could you please clarify the question? You can unmute yourself. You wrote yes. Okay.
Hear me?
Yes,
Yes.
yes.
Yes, my question was basically, you presented the foliation procedure. I think also another possibility of quasi-circle. Is this valid? How does it relate to the Bishop paper and to the possibilities there? Could such foliation, Bishop I think also speaks about this, applied also to other possibilities that he mentions? I hope I understood everything correctly that you presented.
I still can't quite. So what Bishop, he has a lot of results in his paper. And,
but you presented a foliation procedure. Could it be generalized to any of the quasi-circle possibilities that Bishop mentioned?
There's only one possibility. You mean other definition of a Peterson quasi-circle?
So basically,
Yeah, go ahead.
The procedure you developed can then be applied to any of those options that is there. Okay.
Yeah, it applies to any Peterson quasi-circle.
Okay.
So the class of Peterson quasi-circle, first of all, they are Mobius invariant. So the foliation we look at, they're for always shrinking towards zero. So the curve they're required to surround zero.
Yes.
But this is not a very restrictive assumption because they are all invariant under Mobius transformation. You can always move it so that then you have this picture you can fill in by foliation. And okay. This is exactly the same class of a Peterson quasi-circle as in Bishop. But all his definitions, they are equivalent.
Thanks, because I think you also mentioned the 17th possibility, right, in your paper.
Oh, they're not a possibility. They're equivalent as definitions.
True.
Yeah, they're maybe there are other versions of the Peterson quasi-circle in higher dimension that I don't know. There are the Peterson quasi-circle in other dimensions. There's natural definition for them.
Okay.
But
thanks.
They're not the foliation, but they're all equivalent.
Okay, thanks a lot. All clear. A great paper. Thanks.
Okay, thanks. So I think it's time to stop. Okay, because it's 5:07, and so I would again. So before I did some chaos. So now we should thank, I would say, both the speaker. We should thank both speaker. So I would ask everybody to unmute. I will ask everybody to unmute himself herself so that we can thank both the speakers. Okay.
Thank you.
Sorry for the confusion. I'm a little tired. So very nice talk. I have to say it's not my field, but I'm very happy I was able to understand. I think several things. Okay.